When static electrical charge rests upon a three-dimensional object, its final distribution is completely dictated by the object's geometric shape. We are examining a uniformly charged thin spherical shell with a fixed radius, r. In this model, the electrical charge is restricted to the outer skin. The interior volume contains no charge at all. We need to determine how this specific distribution projects its electric field into the surrounding space, both outside the shell and within the empty interior. Outside the shell, the field radiates outward. It behaves as if the entire shell were replaced by a single point charge located at the center. However, inside the shell, the field disappears. The electric force is zero at every internal point. This result, a field that behaves like a point charge on the outside but vanishes on the inside, requires mathematical proof. Calculating these fields typically requires Coulomb's law and the principle of superposition. To use superposition here, you would have to calculate the vector contribution from every individual patch of charge on the sphere's surface to your target point. Integrating these shifting distances and angles across a curved three-dimensional surface makes the calculus exceptionally difficult. We can simplify the problem by utilizing the system's symmetry. Spherical symmetry means that because the charge is uniform, the system looks the same from any angle of rotation. This symmetry allows us to replace exhaustive vector calculus with a more efficient tool, Gauss's law. Gauss's law states that the total electric flux through a closed surface is equal to the net charge enclosed by that surface divided by epsilon naught. To apply this concept, we define what is called a Gaussian surface, an imaginary mathematical bubble used to measure the field. For the math to simplify, the imaginary surface must match the symmetry of the physical object. For our spherical shell, we must use a spherical Gaussian surface that shares the same center. On a spherical boundary, the electric field and the area vector point in the same radial direction. Because they are perfectly parallel, the dot product in our equation becomes simple multiplication. This geometric alignment transforms the integral into a basic algebraic expression, making the field much easier to calculate. First, we will derive the field for a point P located outside the shell. We define our geometry. The physical shell has radius r, and our Gaussian surface has a larger radius, lowercase r. We begin by calculating the total electric flux through this dashed Gaussian sphere. Due to symmetry, the magnitude of the electric field E is constant at every point on the dashed surface. We can pull E out of the integral, leaving us to multiply the field by the sphere's total surface area, 4 pi r squared. The left side of our equation is now E times 4 pi r squared. Now we look at the right side, the total charge trapped inside our Gaussian bubble. Because the surface completely surrounds the shell, the enclosed charge is simply the shell's total charge, Q. Bringing both sides together, we get E times 4 pi r squared equals Q over epsilon naught. Solving for E gives us the final formula, 1 over 4 pi epsilon naught times Q over r squared. This is exactly the formula for a point charge. It proves that for any point outside the shell, the field acts as if the entire charge were concentrated at the center. Next, we derive the field for a point P located inside the hollow shell. We draw a new Gaussian surface with a radius lowercase r that is smaller than the shell's radius, r. Following the same rules of symmetry, the flux through this inner bubble is still E times 4 pi r squared. But we must again determine the amount of charge trapped inside this specific bubble. Since the shell is hollow and the charge is only on the outer surface, our Gaussian bubble contains no charge at all. Mathematically, the enclosed charge for this interior case is 0. When we plug this into Gauss's law, the equation becomes E times 4 pi r squared equals 0. Since the surface area is a positive value, the electric field E must be 0 to satisfy the equation. This derivation confirms that because there is no enclosed charge within the interior volume, no electric field is generated there. This physical principle is exactly why the interior of a hollow conductor is perfectly shielded from external electrical interference. The two rules for a spherical shell are clear. Outside, it behaves like a point charge. Inside, the field is 0. Gauss's law provides a geometric shortcut, allowing us to determine field values based on charge distribution rather than individual vector summation. By identifying the symmetry of a system, we can find direct solutions to complex charge configurations that would otherwise require exhaustive calculations.